This video is brought to you by mywayteaching.com.
In this part, let us study what is torque and angular momentum for a system of particles. Okay, here we are considering not a single particle but rather system of particles. To get total angular momentum of a system of particles about a given point, we need to add vectorially the angular momentum of individual particles, isn't it? Yes. So, the total angular momentum is given by L is equal to L1 plus L2 up to Ln it continues. That is equal to sigma I is equal to 1 to n Li. So this is the total angular momentum of the body. The angular momentum of the ith particle, if you consider, so if you consider the angular moment of a ith particle, then that is given by Li is equal to Ri into Pi, isn't it? Where Ri is the position vector of the ith particle with respect to given origin, and P is nothing but the momentum which is given by what? Yes, that is given by mi into vi. That is the linear momentum of the particle. The particle has a mass mi and velocity vi. We may write the total angular momentum of a system of particles like this also. Means by considering this sigma Li, which is nothing but what? Ri into Pi. We can write in this way also. Okay, so this is a generalization of the definition of angular momentum for a single particle to a system of particles. So using the equation that we studied before, this equation that we studied, torque is equal to R into F, and even using this equation we can get, after differentiating with respect to time, d by dt of sigma Li, that is equal to sigma in other words we can write it as torque, isn't it? Yes, where Ti is the torque acting on the ith particle, and that is given by Ri into Fi. The force Fi on the ith particle is the vector sum of the external forces, because the internal force effect will be zero, as we already know that. Okay, we may therefore separate the contribution of the external and internal forces to the total torque. Means torque is equal to, we'll consider the total torque like this. We can separate the external and internal torque as by considering torque is equal to torque external plus torque internal, isn't it? And this torque external is given by sigma I is equal to Ri into torque external, and torque internal is given by sigma I is equal to sigma I Ri into Fi torque internal. Got this? Yes. We shall assume not only Newton's third law, that is, force between any two particles of the system are equal and opposite, but also that these forces are directed along the line joining the two particles. In this case, the contribution of the internal force to the total torque on the system is zero. Since the torque resulting from each action reaction pair of forces is 0, we thus have torque internal is equal to 0. We know this, right? Torque is equal to torque external. So, we know that torque is equal to sigma from I is equal to N torque I, isn't it? And from the equation we can also write dl by dt is equal to torque external. Thus, the time rate of change of angular momentum of a system of particle about a point is equal to the sum of the external torques. The time rate of change of angular momentum about a particle is equal to the sum of the external force acting on the system taken about the same point. Okay. When only one particle is given, there are no internal forces or torques. At that time, we'll consider it as a rotational analog of dp by dt. That is equal to force external. Okay. So these equations holds good for system of particles, whether it is a rigid body or its individual particles have all kinds of internal motion. So now let us study conservation of angular momentum. If torque external becomes 0, obviously the rate of change of this angular momentum is equal to 0, because dl by dt is equal to torque external and L becomes what? Constant. Isn't it? Yes, thus if the total external torque on a system of particles is 0, then the total angular momentum of the system is conserved. Okay. So this equation, that is L is equal to constant, it is equivalent to these three scalar equations, that is Lx is equal to K1, Ly is equal to K2 and Lz is equal to K3. Here K1, K2, K3 are constants and Lx, Ly, Lz are the components of the total angular momentum vector L along the x, y, z axis respectively. Okay. So this equation, that is L is equal to constant, is the rotational analog of the equation that we studied before. In dealing with this momentum of particles. Okay. That is the rotational analog. This is the rotational analog of this equation. In this case, PO constant, isn't it? Now we are considering dl by dt. Okay. Okay. So now let us study few simple problems. The question is, find the torque of a force 7I plus 3j minus 5k about the origin. Force acts on a particle whose position vector is F is given, R is given here, isn't it? R is what? I minus j plus k. F is 7I plus 3j cap minus 5k cap. So it's very easy to determine the torque that is given by the vector product of R cross F. So we can write this like this by using the determinant form, and here the coefficients of I, J, K and coefficients of F, isn't it? And then we can write by first taking I, this one 5 minus 3 minus of minus 5 minus 7j by considering this minus j, and this one minus 5 minus 7 plus k cap, that is 3 plus 7. So we get it as 2i plus 12j plus 10k. Okay, this is the torque. So now let us see one more problem. Show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. Angular momentum about any point of a single particle, it moving with constant velocity remains constant throughout the motion, which means if you consider angular momentum about a single particle, whole body is moving with constant velocity, then that angular momentum, it remains constant throughout the motion. It will not change at any instant of time. That is what we should prove here. Okay, let us consider one simple figure here. Let the particle with velocity v be at point P. This is the particle that we have considered at time instant t. We want to calculate the angular momentum of the particle about an arbitrary point O. Means after some time interval, we will calculate this angular momentum to prove that it does not change. The angular momentum is given by what? L is equal to R cross mv, isn't it? Yes. And its magnitude is mv r sine theta. We know this. Where theta is the angle between r and v. This is the angle. As shown in this figure, although the particle changes position with the time, the line of direction of v remains the same. Hence, we can say OM is equal to r sine theta. Isn't it? Further, the direction of L is perpendicular to the plane containing R and V. We know this, right? It is into a page of the figure. Perpendicular to this R and V means it is into this page. And this direction does not change with time. Thus, L remains same in magnitude and direction, and it is conserved. Okay. In this case, the angular momentum will not change for different instants of time. It will remain changed throughout the motion of the body. Okay. In the next one, we are going to study equilibrium of a rigid body.